So now let's talk about our mechanical impedance and degrees of freedom. So as I mentioned at the end of the previous video, if we use the idea of impedance for our mechanical components, we simplify our analysis process. And so the way we simplify it is that we're able to skip having to write those differential equations. So this is the exact same sort of approach we took when we were looking at our electrical networks. So in general, we're going to define our mechanical impedances. So mechanical impedances for each of our three basic passive elements we're looking at as mechanical impedance Z sub m. So we have an M subscript to indicate that it's mechanical. It's a function of S because we're in the frequency domain, and we're saying it's equal to the force F of S divided by the displacement X of S. And so what we're going to do then is we can go to that table 2.4. And so our table 2.4 actually already has the impedances listed, but let's say we didn't necessarily have that. So we could go to that table, or from somewhere else, we could take our equations that relate our force and our displacement. So equations for force and displacement, and take the Laplace transform. And again, we could also just look in table 2.4. And these tables will be posted on Canvas as well. But what we'd see is that for our spring, we have a mechanical impedance, Z sub m, which is just equal to K. For our viscous damper, we have a mechanical impedance, Z sub m, which is equal to F sub V times S. And finally, for our mass, we have a mechanical impedance, which is equal to ms squared. So what you could do if you wanted is you could go back and you could work the example from the previous video using this idea of impedances, and hopefully you'd find it to be a little bit quicker to solve. We're going to look, as I mentioned earlier, at some general equations in the next video, and that's going to simplify this process a little bit further. So the other thing that we want to talk about in this video is degrees of freedom. And so ultimately, we're interested in our degrees of freedom because this is the number of equations of motion required. So number, let's see if I can't draw that a little better. So number of equations of motion required. So basically, if we're looking at a system, it's going to tell us how many equations we need to write. Similar to how I talked about essential nodes being useful to identify in order to know how many equations we need if we're doing node voltage analysis. So this degrees of freedom is also equal to our number of linearly independent motions. Linearly independent motions. So for my fellow double E's, maybe it's again been a while since you've dealt with this stuff, so it doesn't make sense, or maybe you don't quite remember. And basically what we're saying is this linear independence is that a point of motion in the system can still move if we hold all of their points still. So a point of motion in a system can still move if all other points of motion are held still. And so again, the main point here, hopefully that helps you kind of get an idea of what degrees of freedom are. We'll talk about it in the next couple examples that we'll do throughout the rest of this unit. But the basic idea is that we're using this degrees of freedom to find out how many equations we're going to need to write. If this is a little muddy, particularly to some of you double E's, there is an analogy given in the textbook to a sort of multi-mesh circuit, which sort of kind of corresponds to this idea of linearly independent motions. We could talk about linearly independent currents with both the circuit and our mechanical systems. Ultimately, when we are if we look at these things piecewise, as far as one point of motion at a time or one mesh at a time, we ultimately then come back and put all of these pieces together using superposition to get our overall answer.